This is section 8.4, vectors. We're going to begin by interpreting vectors geometrically. So there's a few things we need to talk about. We're going to first be talking about scalars, and scalars are quantities described by a single value called the magnitude, and the magnitude is the size or the measure of the quantity. Then we're going to be talking about vectors, and those are quantities that are described by both magnitude and direction. So for example, the speed of an object is a scalar quantity that tells us how fast an object travels. The velocity of an object is a vector quantity because it tells us how fast the object travels and in which direction it travels. Okay, so that is the difference between a scalar and a vector in example. So a vector in a plane is a line segment with a direction. So you're given a specific direction with a line segment. So looking over to the right, we have vector PQ. And as you can see, there are endpoints P and Q. The endpoint P is the initial point, and the endpoint Q is the terminal point. How can you tell that? By this arrow right here. And that's how you know the terminal point. The magnitude is noted as this, and there's usually two vertical lines, magnitude, on each side of the vector notation. You can also see it here. And this is the length of the line segment. And using the context of displacement of an object, the vector PQ refers to the object's overall change in position, moving from P to Q. I think that is a really, really good context to talk about. The overall change in position, that is displacement. Okay, and that's really what this vector refers to. Now, when would you have two vectors that are equal? Two vectors are equal when they have same magnitude and same direction. So look at all of these vectors here in this example. All of these vectors are equal. Why are they all equal? They're all equal because they have the same magnitude and the same direction. Okay, for vectors, we often use boldface lowercase letters. And you can see some examples here. We might use U, V, and W. So if, for example, V is equal to vector AB, V represents the set of all vectors that are equal to vector AB. So it's really, really important. It's just not that single one. It could be similar to this diagram where we have other ones. Because it's difficult to depict handwritten boldface, we will sometimes use an arrow over the letter. So keep in mind that this arrow over the letter is the same as a boldface V, okay? And that's how we will write a vector. Okay, determine if these two vectors are equal. So V, let's go ahead and take a look, from negative 3, 1, there's their initial point, to 1, 4 is the terminal point. And that's vector V. And then W is from 0, negative 3, to 4, 0. And what do you notice? vector W and vector V have the same magnitude and the same direction. Looking at the next example, vector A, let's take a look at that, from -4, -2 to -1, -4. So there is vector A. Vector B from 4, 2 to 1, 4. And as you can see, these vectors are not the same. They look like they have the same magnitude, but they have different direction. So therefore, no. Okay, let's go ahead and talk about the sum of two vectors. So, if vector V represents the displacement from P to Q, you can see that right here, and vector W represents the displacement from Q to R, then vector V plus W represents the displacement from P to R. So the vector V plus W is formed by placing V and W tip to tail. So the initial point of W is placed at the terminal point of V. Okay. The sum V plus W can also be visualized by placing V and W at a common initial point, and we call this tail to tail. And the sum V plus W is the diagonal of the parallelogram from the initial point of V and W to the opposite vertex. Okay, so we can have both of those seen just like those diagrams, and the vector, the opposite of vector V, is the same as -1 times V. Here we have the same magnitude but opposite direction. If we do use the opposite direction of a vector, we can define that as subtraction. So the difference of vectors V and W is given as V minus W is V plus the opposite of W. If a vector V is multiplied by a real number K, the magnitude of KV is the absolute value of K multiplied by the magnitude of vector V. The direction of K times V is the same direction as V. And this is always the case if K is positive, and it's in the opposite direction if K is negative. Okay? The value K is a scalar, and for this reason, the vector KV is called a scalar multiple of vector V. The value of K either stretches or shrinks the length by a factor of the absolute value of K. And you can see that over here to the right, we have V and 2V. We also have 1/2 V. Now look at this difference here. The opposite of 2V and the opposite of 1/2 V. So you can see this change in direction. with that negative, okay? And here you can see the change in magnitude. Okay, now what if k is equal to 0? Well, then kv is what we call the 0 vector, and it is denoted as 0 boldface, or we could write 0 vector. The 0 vector has a magnitude of 0 and has no direction. So a vector sketched with initial point at the origin of a rectangular coordinate system is said to be drawn in standard position. So that's the initial point is at the origin. So we're going to sketch u plus v by placing the initial point of u at the terminal point of v. So let's do that. We're going to take u and we're going to put the initial point of u right here, but we're going to place that at the terminal point of v. And as you can see, that will look like this vector here. And then what happens? Now, I'll change colors. We have u plus v. Okay. Now in number 3, we're going to sketch u plus b by drawing u and v with the same initial point. And then we'll take a look at that parallelogram. So let's go ahead and write u with this same initial point. So this would be this same initial point. And as you can see, we travel 1, 2, 3, 4, 5, 6, 7 units down, and it looks like 1, 2, 3 units to the right. So 2 to 5, and it looks like it would be right here. And let's see, 1, 2, 3, 4, 5, 6, 7, 8. That's where I made a mistake. 1, 2, 3. Okay, so I think I can grab that. So I'm going to go down 8 units and then 3. There we go. You can see how that looks much better. And that is u. And now, what are we going to do? We're going to go ahead and sketch these different sides to create that parallelogram. So you can kind of see where I would go ahead and sketch it like this. It's not going to be perfect. But what am I looking for? I'm looking for this right here where I could find that diagonal. And now I could say that this is u plus v. I didn't do the best job there, but I guess you can kind of see that. Made it a little bit too long. Okay. Looking at number 4, we're going to sketch v minus w by drawing v and w with the same initial point. So let's go do that. So we will have w here, and w is right here, and it goes down 1, 2, 3, 4, and to the right 2. And so here is w. And then we are going to have v minus w. So we're actually going to be pointing to w. To v this time instead of w. Pointing to v since we have that v minus w. So we will just draw it like that. Okay, so that actually points to V. Okay. Let's look at number 5. We're going to sketch negative 2V and 3W in standard position. So meaning we're going to the origin with each one of these, and then we will multiply vector V by the scalar negative 2 and 3, and W by the scalar 3. So let's see what we have. Let's start with W. So if we have W, we want to multiply it by 3. You can see here that if we have both sides here are 2 units, we are now going to have 6 units on each side. So we're going to go ahead and put 3W here. And there we have it. That is 3W. Okay, let's take a look at V. And as you can see, I don't know why that didn't type that right. And looking at V, as you can see, if we're going to have negative 2 times V, we will go ahead and turn in the other direction. And here we had 2 units before, now we will have 4. And here we had 3 units, so this will be 6. So now we will turn the other way, go in the opposite direction due to that negative 2. So now we can go ahead and take this here, about right here. And this is negative 2 times vector V. Okay, now let's represent vectors in component form. So we have 2 points in the plane P and Q, and we're going to let vector V have its initial point at P and its terminal point at Q. The component form of vector V is given as x2 minus x1 as the x component and y2 minus y1 as the y component. And you can see that AB in vector notation is not the same as point notation. So we do need to be very, very careful with that. Okay, so given vector V with initial point 3, 8, let's call that point 1, and terminal point negative 1, 3, we're going to find the component form of vector V. So vector V is going to be equal to negative 1 minus 3, and then 3 minus 8. And that's equal to negative 4, negative 5. In number 7, given vector V with initial point 12, negative 10, and terminal point negative 20, 10, find the component form of vector V. So vector V is going to be equal to, we have negative 20 minus 12, and then we have 10 minus, and we have to be careful here, a negative 10. And that's equal to negative 32, 20. Okay, if this vector V is placed with initial point at 5, 3. So this is the initial point. What would the terminal point of V be? Well, our terminal point would be 5 minus 32, and then we would have 3 plus 20. So that point is equal to negative 27, 23. Again, these are points written as coordinates and not component form. Okay, now we're going to be performing operations on vectors, and we're going to be doing this in component form. So we do have the equality of vectors. If vector v and w are equal, they are if and only if equal, if a1 equals a2 and b1 equals b2. And operations, if we are going to add vectors together in component form, we can just add each one of these parts together. Subtraction is the same, and note the scalar. So each component can be multiplied by that scalar. Here are the properties if you want to take a look at these. Of course, you can see that we have distribution working. 0 times any vector is 0. If v plus w is the same as w plus v, we can rearrange our terms. If we add the 0 vector to any vector, we come up with that vector again. And you can look at these. You can also see that a constant times a vector in magnitude, this is magnitude of a constant times a vector. It's the same as that absolute value of that constant times the magnitude. And you can go ahead and take a look at all of these. So let's begin with these examples. If we're given vectors r and s in component form, you can see that this is just equal to 1 plus 2, adding the same coordinates together, and we will have 3, negative 1. In number 9, we will have negative 4 times the component form of vector s, and we have negative 8, negative 12. In number 10, we will have 3 times vector r plus 2 times vector s. So here we will have 3, negative 12 plus 4, 6. And now we could add those components together, and we will have 7, negative 6. Okay, now we're going to represent vectors in terms of I and j instead of component form. So the unit vector is the vector with magnitude 1. That is what we call a unit vector. And the magnitude of any vector AB component form is the square root of a squared plus b squared. So to find a unit vector in the direction of a given vector, so if we're looking for one in the same direction of a given vector, we will use this formula here below. So we've given vector v in component form. Then a unit vector, so a unit vector u, and we will use that little subscript, is equal to 1 divided by the magnitude of v times vector v. You can see the component multiplication, and now you can see where that magnitude of vector v is divided by both of those components. So let's try in number 11 to find a unit vector u in the direction of w, and they've given w as negative 8, 15 in component form. And then we're going to verify that it is a unit vector. So let's begin with the magnitude of vector w. And that's going to be equal to the square root of negative 8 squared plus 15 squared. And here we come up with 17. So this unit vector in the direction of w is equal to 1/17 times vector w. And that's equal to negative 8/17, 15/17. Okay, there are two very important vectors, and they are I and j, because they are unit vectors in the direction of the positive x and the positive y axes. You can see them right here. Here is I and here is j. So the representation of vector v in component form, when we write it in terms of I and j, is ai plus b times j. And the values of a and b are called the scalar horizontal and scalar vertical components of v. So let's try to write vector v, negative 12, negative 30, in terms of I and j. And that is going to be equal to negative 12i minus 30j. And we can go ahead and write those vectors above. Keep in mind that vector I is not equal to the number I. This is a number. This is a unit vector. Okay, so now we're going to relate the component form and the direction and the magnitude of a vector. So let's look at all of this together, and you can see we now have theta, which is now our direction angle, and it is measured counterclockwise from the positive x-axis, okay? It's always going to be over this interval, 0 to 2 pi or 0 to 360 degrees. So there you can see the direction angle. You can see the I and j components of the vector, and you can also see this magnitude. Okay, and here are our scalar components, A and B. Okay, so then we will be able to write vector v in component form or in our I and j form, representing them with I and j. Okay, in number 13, we're going to write the vector v in the form ai plus b times j, where v has magnitude of 10 and a direction angle of theta equal to 3 pi over 4. So let's begin with A, and A is going to be 10, that magnitude, multiplied by the cosine of 3 pi over 4, and that's equal to the opposite of 5 root 2. And B is going to be equal to 10 multiplied by the sine of 3 pi over 4, and we will have 5 root 2. And now we have vector v is equal to the opposite of 5 root 2I plus 5 root 2j. In number 14, we're going to find the magnitude and direction angle for S equals 7I minus 3j, and we are going to round to 1 decimal place. So let's go ahead and begin with the magnitude of vector S, and that's going to be the square root of 7 squared plus negative 3 squared, and that's going to be the square root of 58. And we also know that vector S is in quadrant 4. Now, how do we know that vector S is in quadrant 4? Because we're 7 in the I direction, negative 3 in the J unit vector direction. So it will look something like that, okay? So maybe I should draw a little bit larger axes. I think it might be nicer. And so we have a magnitude of root 58. And we are in quadrant 4 because of the values of I and j. So we have the tangent of theta. So you can see that theta will begin here and come all the way around. So that's what theta is going to be. Okay? And what will we have? We'll have the tangent of theta is going to be the opposite of 3 over 7. So if we take the inverse tangent of both sides, we should come up with about 336.8 degrees, or we could have a negative 23.2 degrees. And you can see that here also. Okay. So, move some of this over. In number 15, we can see that a baseball is thrown with a speed of 65 miles an hour at an angle of 12 degrees from the horizontal. Let's just go ahead and get something sketched because it will make it easier for us. So here we have theta equals 12 degrees, okay? So now let's take a look at the magnitude. Let's keep reading. Write the velocity vector v at the time of release in terms of I and j, and then we will round to the nearest tenth of miles per hour. Okay, so that magnitude of vector v is 65, since that's what they gave us. And we were also given that theta is 12 degrees. We know that vector v is going to be equal to a times I plus b times vector j. So we have a equals 65 times the cosine of 12 degrees, and that's about 63.6 degrees. And then we have b equal to 65 multiplied by the sine of 12 degrees, and that's about 13. Whoops, this was not supposed to be degrees, 63.6. It is a scalar. So therefore, vector v is equal to 63.6 I plus 13.5 j. Now, using vectors in applications can sometimes make these problems a little bit easier. So let's see what we have here in number 16. A boat travels 10 knots at a bearing of 25 degrees west of north in still water. It encounters a current moving due west at 3 knots. Find the true speed to 1 decimal place and the direction of the boat. Okay, so let's go ahead and take this one step at a time. So as you can see, we had 90 degrees here, plus we had another 25 degrees. So that is where we came up with 115. And now we can see the velocity of the boat in still water is given by, and let's go ahead and write that out. The velocity of the boat, that vector, is going to be 10, because that's its speed, 10 times the cosine of 115 degrees I plus 10 sine of 115 degrees j. That is velocity b. Whoops, I don't want to write on that. That is that vector there, okay? Now, how about the velocity of the current? If the current is moving due west, that velocity of the current is going to be -3 times vector I. So the net velocity of the boat is going to be the sum of these vectors. So vector v is going to be equal to the vector of the boat plus the vector of the current. And that's going to be equal to 10 cosine 115 degrees I plus 10 sine 115 degrees j plus a -3 I. So as you can see, we will have 10 cosine 115 degrees minus 3 times vector I plus 10 sine of 115 degrees times vector j. And if you would put this in your calculator, you would get approximately -7.2 I plus 9.1 j. Okay, now they asked us for the true speed and the direction. So we're going to need to get both of those. So let's go ahead and begin with the true speed. And that true speed is the magnitude of our vector v. And as you can see, that's going to be the square root of -7.2 squared plus 9.1 squared. And you'll get about 11.6 knots. Okay, how about the direction of the boat? Well, we know that the tangent of theta is going to be equal to 9.1 divided by -7.2. So we know that theta is the tangent inverse of that quotient. And that comes out to be approximately negative 52 degrees. So if we are in quadrant 2, we have 180. So let's go ahead and write this here. If we are in quadrant 2, we will have 180 minus 52 degrees, and we will have 128 degrees. Okay. Okay, let's look at our last problem, and we will have forces in units of pounds, and we have 2 force vectors, actually 3. And all 3 of these forces act on an object. Force 1, force 2, and force 3. And we want to find the resultant force. And that is just going to be each one of these forces added together. And here we will have 10I minus 3j plus negative 2I plus 1j plus 11I. And I probably don't need those on that. And so now we come up with 19I minus 2j. And that is that resultant force R. So what additional force? So we're looking for an additional force is needed for the object to be in static equilibrium. So for the object to be in static equilibrium, we need to find the opposite of that vector. So that would be negative 19I plus 2j. And that concludes this section.